Good morning, everyone. Thank you for joining us today. In our last deep dive, we talked all about the privacy paradox. Well, today we're shifting gears to what is, arguably the most critical risk mitigation strategy in AI, that partnership between the machine and its human operator. This isn't just some design choice, it's a fundamental architectural and, frankly, ethical decision. We're going to move beyond that sci-fi dream of a perfect, infallible AI and get right into the practical, essential reality of human-machine teaming, exploring the engineering, the psychology, and the real-world stakes of getting this balance just right. This quote right here, it just frames our entire discussion perfectly. The goal isn't to replace human intelligence, it's all about augmenting it. It's about designing systems that don't push us out of the decision-making process, but actually invite us in at the most critical moments. What we're really aiming for is a kind of synergy, right? Where the machine handles the brute force computation and data processing at a scale no human ever could, and we, the humans, provide those irreplaceable elements: context, ethical reasoning, and ultimate judgment. Today, we're going to explore exactly how to engineer that partnership. So let's dive in. All right, here's our roadmap for this explainer. We'll kick things off by defining what meaningful human control actually is, a term that started in military ethics but is now totally central to all high-stakes AI. Then we'll explore the spectrum of oversight through three key architectural models. After that, we have to talk about the dangerous psychological trap of automation bias. From there, we'll pivot to the solution, the core engineering and design principles for building truly collaborative systems. We'll ground all this with some real-world examples, and we'll finish up by crystallizing the human's ultimate, non-negotiable role in this new era. So let's get right into it with our first core question. What is the principle of meaningful human control? It's a term we hear thrown around a lot in AI ethics and governance, but what does it actually mean in practice for the engineers and system designers building these things? The crucial point here is that this isn't some binary on or off switch. It's a whole spectrum of engagement. Good AI governance and really good system design demands a risk-based approach. You have to deliberately choose the right level and the right type of human involvement based on the stakes of the decision. The higher the potential for irreversible harm, think medicine, aviation, or finance, the more direct, informed, and timely that human control has to be. And this means the human operator can't just have the ability to intervene, they've got to have the situational awareness to know when and how to intervene effectively. Okay, so that brings us to our next question. If it's a spectrum, what does that spectrum actually look like from an architectural point of view? Let's break down the three key models of human oversight that really define these different levels of engagement. Now, what's so interesting here is how this lays out the really distinct architectural and operational roles. First up, we have human in the loop, or HIT. Here, the human is an active collaborator, a mandatory gate in the whole process. The AI does the heavy lifting. Maybe it's analyzing thousands of legal documents or screening candidate resumes, but it only ever makes a recommendation. The final binding decision, that's reserved for a human expert who has to take an explicit action to say yes or no. This model is absolutely essential for high-stakes, ambiguous tasks where context and nuanced judgment are everything. Next is human on the loop, or hot loop. In this setup, the human is more like a watchful supervisor. The AI is in direct control of a process. It's flying the plane, driving the car, or monitoring a network for threats. But the human is actively monitoring, ready to intervene if the system hits an edge case it can't handle. The whole system is designed for the human to take over, which makes the quality of the user interface and that handover protocol absolutely critical. And finally, there's human over the loop, or HUTE loop. In this model, the human acts as a strategic commander. They set the high-level goals and constraints beforehand, like setting the budget and target audience for a massive ad campaign. Then the AI goes off and executes thousands or millions of actions on its own. The oversight here happens after the fact by looking at performance dashboards and tweaking the system's strategy, not by approving every little action. But that human on the loop model, which is so essential for things like autonomous vehicles and modern aviation, well, it hides a deep psychological trap. And this brings us to a really critical question. What is automation bias, and why is it so incredibly dangerous from a systems safety perspective? This is a really well-documented cognitive bias. See, when a system is highly reliable, it works perfectly 99.9% of the time, our brains naturally lower their guard to save energy. We switch from active critical monitoring to just passive observation, and we start to just assume the computer is always right. This leads to two types of failures. First, errors of commission, where we blindly follow a wrong suggestion. Think of a stock trading algorithm executing a flawed trade because the human operator just reflexively clicks approve. But second, and even more insidious, are errors of omission, where we fail to notice when the system makes a mistake or silently stops working, simply because we've stopped paying close attention. Our situational awareness just degrades. And this perfectly illustrates two related problems that compound each other. Skill atrophy, or deskilling, is what happens when we outsource a cognitive task to a machine for too long. A pilot who rarely flies manually, or a network engineer who always relies on an automated diagnostic tool, might find their own fundamental skills have gotten weak. Their cognitive muscles for that task just start to decay. And this feeds directly into the irony of automation. The better and more reliable the system gets, the less we have to do, and the less engaged our brains become. This means the system's very own reliability makes the human operator less prepared and less capable for that one critical moment when the automation inevitably fails and hands control back. The system's greatest strength becomes the partnership's greatest vulnerability. To really understand the real-world consequences, we have to look at the tragic case of Air France Flight 447. The Airbus A330 was flying on autopilot through a storm when its airspeed sensors, the pitot tubes, iced over. This was a classic edge case the autopilot wasn't designed for. So, just as it was programmed, it disengaged and handed control back to the pilots with a bunch of alarms. In that moment of shock, with their situational awareness totally degraded by hours of just passively monitoring, the co-pilot, likely disoriented, pulled back on the controls. This action, a basic error, put the plane into a steep climb and caused an aerodynamic stall. And even though stall warnings were blaring for nearly a minute, the crew, suffering from the effects of automation bias, never fully grasped what was happening. They had lost the feel for their own aircraft. 228 people lost their lives. This isn't some theoretical risk from a research paper. This is the real-world price of a breakdown in human-machine teaming when the stakes are absolute. The official investigation concluded that this wasn't just pilot error, but a failure of the human automation system as a whole. This quote from an analyst just cuts right to the bone. The investigation revealed that while, yes, human error was the final link in the chain, those errors happened in the context of a highly automated system that failed in a deeply confusing way. The pilots were thrown from being passive monitors to active controllers in a high-stress environment without the deep situational awareness and practice skills they needed to solve a fundamental aerodynamics problem. It is a chilling, foundational lesson. The handoff from machine back to human is the most perilous moment in any automated system. Okay, so that's the problem. How do we solve it? This brings us to the core principles of designing for effective human-machine teaming, designing to avoid these very traps and to build systems that are resilient, not brittle. This requires a completely new design philosophy, one that builds systems for collaboration, not just automation. These 4 principles are really the guide to turning a simple tool into a true AI teammate, creating a synergy where the whole is so much greater than the sum of its parts. Let's break them down. The first 2 principles are the bedrock of building appropriate trust. First, explainability, or XAI. A collaborative AI can't be an opaque black box. It has to show its work. An AI tool for radiologists shouldn't just spit out cancer detected. It has to highlight the specific region on the scan that it finds suspicious, and maybe even show similar examples from its training data. This gives the human expert the evidence so they can rapidly verify the reasoning. Second, the AI must communicate its own uncertainty. One of the most dangerous failure modes is an AI that is confidently wrong. A trustworthy partner needs to know what it doesn't know and be able to express that uncertainty to its human counterpart. This is a great way to visualize it. An AI that provides a calibrated confidence score lets the human manage their own attention. A finding with 99% confidence might just need a quick check, but one with only 55% confidence immediately tells the human expert, hey, look closely here, I'm not so sure. And when it's faced with something completely new, an off-distribution input that looks nothing like its training data, it should be programmed to simply defer, to say, I have no idea what this is, you take over. This allows the human expert to focus their valuable brain power where it's needed most, on the complex, novel, and ambiguous cases. The next 2 principles are all about creating true synergy. Principle 3 is building feedback loops. When a human expert corrects the AI's mistake or refines its suggestion, that correction is an incredibly valuable piece of new data. The system has to be designed to capture that feedback seamlessly and feed it back into the model for retraining, usually through a robust MLOps pipeline. This creates a virtuous cycle where the human expert is constantly teaching and improving their AI partner. And the final principle is engagement by design. To fight skill atrophy and automation bias, the user interface itself should require active participation, not just passive observation, keeping the operator vigilant and in the game. All right, this all sounds great in theory, but how does it actually work in practice? Let's explore how two high-stakes domains, the modern airliner cockpit and AI and radiology, are modeling this collaboration out in the real world. Here we see two brilliant but very different success stories. The modern cockpit is a mature example of the human-on-the-loop model. In response to tragedies like AF447, the industry has really doubled down on training. Pilots now spend enormous amounts of time in simulators, practicing not just routine flying, but specifically how to manage complex automation failures. The systems themselves are designed to be more transparent, showing pilots exactly what the automation is doing and why. In contrast, the radiologist co-pilot is a powerful human-in-the-loop model. The AI doesn't replace the doctor, it supercharges them. It does the tireless, repetitive job of pre-screening hundreds of images, flagging potential issues the human eye might miss due to fatigue. This frees up the human expert to apply their deep medical knowledge to the most complex cases and make that final, critical diagnosis. We have covered a lot of ground today, from defining control to the psychology of bias and the principles of good design. This brings us to our final summarizing question: what is the key takeaway about the human's role in the machine? And this quote, it just perfectly encapsulates our core takeaway. The goal of most successful, safe AI isn't full, lights-out autonomy. It's about effective augmentation. It's about building a partnership where the AI handles data at scale and a human provides the context, the ethical guardrails, and the ultimate judgment that you just can't program into an algorithm. So to quickly summarize our key takeaways, we've seen that meaningful human control is a spectrum, and choosing the right point on that spectrum, from hit-till to hot-till to hoot-till, is a critical design decision. We've confronted the profound danger of automation bias, so tragically illustrated by AF447, where a system's reliability can become a source of human vulnerability. And most importantly, we've laid out the 4 design principles for true collaboration: building trust through explainability and uncertainty communication, and creating synergy through feedback loops and engagement by design. The goal is always augmentation, not replacement. Now, building these collaborative systems is the responsible path forward. But as we've seen, this technology is powerful, which means, of course, it can also be misused. That's why in our next explainer, we're going to turn our attention to the dark side of AI: deepfakes, disinformation, and deception. Thank you so much for joining us for this explainer. I hope it provided a clear framework for thinking about this critical topic. To continue the journey with us, please subscribe to our channel, Tech, AI, and Beyond. We'll leave you with a question on your screen to think about. As AI gets better and better at handling the data, what judgment is truly uniquely ours to keep?